Okay, so hello everybody. Today we have with us Victoria DiTomasso. She did her undergraduate studies at the City University of New York, Hunter College. While in college, she studied brown dwarfs at the American Museum of Natural History before graduating with her bachelor's degree in physics in 2018. She spent a year as a Fulbright scholar studying M dwarf metallicities at the Leibniz Institute for Astrophysics in Potsdam, Germany, before starting her PhD at the CFA in Cambridge, Massachusetts. She is now a fourth-year PhD student at Harvard, working with Dr. Mercedes Lopez Morales and the HARPS North collaboration. And she characterizes small exoplanets using precise radial velocity mass measurements. She's going to tell us today about this work. So thank you very much for being here, Victoria, and whenever you're ready.
Great. Thank you so much for the introduction. I'm really sorry that I wasn't able to be there in person with all of you today, but I'm excited to get to tell you a bit about my work characterizing small warm exoplanets via precise radial velocity mass measurements. There we go. So this I was hoping to do in the room. I wanted to get a bit of a gauge of the audience, because I know some folks at the Institute are experts in using stellar radial velocities to measure exoplanet masses, but there also might be some folks who are not super familiar with this. I might go out on a limb and ask if folks want to turn on their cameras for like a moment and indicate to me if this is something that you do or have done for your research. Put up one finger. If this is something you're familiar with, but you haven't necessarily done yourself, put up 2 fingers. And if it's something you're not familiar with, put up 3 fingers. Also, if you don't want to do that, I understand. Okay. Okay. Great. Well, thank you for your participation. I appreciate it. So some of this is going to be review for those of you that are more familiar with this, but just as an overview of the radial velocity method, how this works is that we make repeated spectroscopic observations of a star over time. We measure the spectrum and we measure the Doppler shift of the star at that time in order to determine its radial velocity, and ultimately make a plot like what's shown on the upper right here, where we have the velocity of that star over time, where we can look for this characteristic Keplerian shape that would indicate to us that the star is doing its little wobble because there is a planet orbiting around it. And if we measure the semi-amplitude of the signal, or how much the star is wobbling, if we also know the mass of the star, we're able to use Kepler's laws to measure a mass for that planet. Now, another kind of broad overview plot I wanted to start with is this one of sort of the exoplanet landscape. Now, this is showing the number of exoplanets discovered over the years, where they're colored by the discovery method. So you can see that in the early years of exoplanet discoveries, they're all being found using this radial velocity method. But as we get into the era of Kepler, K2, and TESS, the number of planets being discovered by transits greatly outnumbers the number of planets we're discovering using the radial velocity method. And transits are really great, as even when we're talking about small exoplanets. So when I say small, I'm referring to planets smaller than about 4 Earth radii or smaller than about 30 Earth masses. And using the radius measurements we're able to get from transit observations, we're able to start discovering some population-wide characteristics of these small planets. For an example, the radius valley. So we're able to see that these small planets organize themselves into 2 general populations of super-Earths and sub-Neptunes. Also using transits, we're able to get transmission spectra and start characterizing the atmospheres of small planets. So this is a result from James Webb that came out very recently, a transmission spectrum of an Earth-sized planet, LHS 475b. So in this way, transit observations are helping us get at the bulk properties and atmospheric compositions of these small planets. But I think it's worthwhile asking how masses can help contribute to this picture. So the first thing I want to mention is that precise masses are necessary in order to determine bulk densities of these planets. And we're going to need bulk densities if we want to determine the bulk compositions for these planets. So on this plot, I'm showing the mass of small planets versus their radii. And these are all of the small planets on the Exoplanet archive that are listed as having masses that are measured to lower than 20% precision. I've also included a number of common compositional models on this plot. So we have our rocky planets, our water worlds, and then our rocky cores with hydrogen envelopes. So you can see how we need precise radius and precise mass measurements in order to start fitting these composition models. We also need masses in order to interpret atmospheric observations for these small planets. I want to spend a couple slides talking about this result from Battaglia et al. 2019, where they took 7 example planets. They produced synthetic JWST transmission spectra and then performed retrievals on those synthetic spectra, assuming different levels of knowledge about the mass of that planet. So I'm starting off here showing the posteriors for their retrievals of the temperature and metallicity of a warm Neptune planet. And the top row is showing the posterior when they assumed that they knew the mass of this planet with 100% precision. So they just knew it, followed by if they had an uncertainty on their mass of 20%, 50%, 100%, and if they didn't have a mass measurement at all. And what this test showed them was for this sample warm Neptune planet, the precision of the properties they were able to retrieve from an atmospheric observation decreased when they didn't know the mass very precisely. They also did this for a warm sub-Neptune planet. And for this case, they found that both the precision and the accuracy decreased. So as they knew less and less about the mass of the planet, the uncertainty on the values they're able to retrieve for temperature and metallicity increased. And in some cases, they retrieved an entirely incorrect value. And the last example from this paper I'm going to share is their terrestrial planet, where they found, again, the precision decreased and that they were unable to constrain the composition of the atmosphere, which in this case, they used log H2O mixing ratio as a proxy. So when they had no mass at all for this small planet, they weren't able to retrieve that value from their synthetic spectra. So all of this is to say that even with James Webb, we're going to be getting these awesome atmospheric transmission observations, but we need these mass measurements in order to interpret those observations and actually learn about the atmospheres of these planets. Now, the last kind of background thing I want to say before I get into my own work is that detecting small planets in radial velocities and measuring their masses is a challenge. So I wanted to share here the radial velocity phase curve for a hot Jupiter, one of the early ones, HD 130322, discovered in the year 2000, which has a semi-amplitude of 0.1 kilometers per second. So these hot Jupiters and larger mass planets, once you have the stellar radial velocity measurements, it's on the straightforward side of being able to detect and measure the masses of larger planets. But as we start pushing down to smaller planets, so this is an example from one of my projects, which I will be talking about in a lot more detail in just a moment. This is a 10 Earth mass planet that has a semi-amplitude in the radial velocities of only 3 meters per second. So we've got order of magnitudes difference there. And also for these small planets, we need to start worrying about the effects that stellar activity has on our radial velocity measurements. So here on the left, I'm showing a cartoon image of a star that is rotating, and the star has a cool spot on it that is rotating in and out of our view. It's also showing how the shape of one spectral line changes as that spot rotates in and out of our view. And this change is going to affect the radial velocities that we measure from the spectra of active stars. So here's an example of how if I didn't include a stellar activity model when trying to measure the mass of this particular planet, you can see the scatter on the radial velocities increases quite a lot. And I think out of this, I wouldn't be able to detect the planet to a sufficient sigma. So for the rest of the talk, I'm going to be telling you about two projects that I have worked on. The first one is HD 79211b, also known as GJ338b. This is a planet that is not known to transit its star, and it's about, well, its minimum mass is about 10 Earth masses. I published this result earlier this year. And then the second project I will be sharing with you is trying to get a mass measurement for GJ341b, also known as TOI 741. This is a candidate planet that was discovered in TESS. It's got a radius of about 1 Earth radius, and it is a JWST atmospheric target. And this project is still in progress. To start off with HD 79211, it is an M0 star that is in a gravitationally bound binary with another M0 star. And there was a planet detected and published by González-Álvarez et al. 2020, who I believe is on this call. And they used 3 seasons and 159 CARMENES radial velocities to discover and measure the mass of this planet that has a period of 24.4 days. Now, I'm a member of the HARPS North collaboration, and HARPS North had been monitoring this star for a number of years as part of its Rocky Planet Search program. This is the program by which the collaboration monitors bright, quiet stars in an effort to discover longer period small planets in radial velocities. And the HARPS North and the CARMENES data sets, which I have plotted here, the CARMENES is in orange and the HARPS North is in blue. They're quite complementary data sets because the HARPS North data has smaller uncertainties and a longer baseline, but fewer points in each season, whereas the CARMENES radial velocities have larger uncertainties, but much better sampling in each season. So my goal in trying to confirm the presence of this planet in the HARPS North radial velocities, I had to answer a couple questions. Like, did we see this 24.4 day periodic signal in the HARPS North RVs? Is it possible that that signal is an effect of the binary? Is it something that could be a fluke of the data? So something like an aliasing effect, which is caused by the observing cadence interacting with physical periodic signals in your data? Could it be caused by the star's rotation or stellar activity? And is this a periodic signal that we see in the different data sets? So the benefit of my analysis that I have the HARPS North and the CARMENES RVs to work with. So to start off, I'll address the stellar binary. So here I am showing, again, the HARPS North and the CARMENES radial velocities, and also including these high-res radial velocities. So there were just a few high-res data points per season, but altogether, this gives us a baseline of about 25 years. And this dotted line is showing this overall trend, and that is being caused by the stellar binary. In the González-Álvarez paper, they did something that I think was super cool, which is that they were able to model the stellar binary using astrometric and RV measurements dating back as far as 1821. They were able to fit this stellar binary's 1300-year orbit. But what they found was that over the short baseline of the CARMENES radial velocities, a line did just as well modeling the binary over that time scale. For my 25-year baseline, I used a second order polynomial, but with just a very small curvature, and all of this is consistent. So then the next question is to ask, if I see this 24.4 day periodic signal in the HARPS North radial velocities, and one way to check that is by looking at a plot like this, which is a periodogram. Now, to take a moment to orient in case this isn't something you're used to looking at, periodograms tell us how periodic our data is at different frequencies. So here I have frequency on the bottom axis and the corresponding period on the top axis in days. And the peaks, if they come up above these horizontal lines, which are our false alarm probability lines, that means that the periodicity that we see in that data is likely real and not just random, kind of within the uncertainties of the data. And here's a little zoom in panel. So we have 2 significant periodic signals in the HARPS North RV data set after subtracting the effect of the stellar binary. one at 24.4 days, which is great, and also one at 24.7 days. Now, the next question is to check if there are aliasing effects or how aliasing effects are manifesting in our data. So again, this is how the observing cadence can cause periodic signals in the data, as opposed to those periodic signals being representative of something physical in the system itself. So what I chose to do to test this is to make another periodogram. But here I also included a periodogram for a Keplerian model with a period of 24.4 days at the sampling of the HARPS North dataset. So for the Keplerian model that just has that and nothing else going on, the peaks are a lot stronger, but the shapes of the peaks mimic the shapes of the peaks in the data, the periodogram of the data, quite well. And so, for instance, this convinced me that the 27-day significant periodic signal is in fact an aliasing effect, because we also see it in a periodogram of just a plain Keplerian model. Another question that's good to ask is if this periodic signal could be the rotation period of the star itself. And if we're interested in finding the rotation period of a star, it can be really helpful to have light curves for that star. Now, for this particular target, that presents some challenge, and that's because HG 79211 is in this stellar binary with HG 79210. So they fall very close to one another on the sky. They're only 17 arc seconds apart. So they're blended in a lot of photometric surveys like TESS, where we might normally turn to get these light curves. So what I did was that I used Kepler-TAM, which is on a telescope in Arizona, to get new photometric measurements. So I'm showing an image of that here. So we have HG 211 and its binary companion up here, and we have a number of comparison stars in the field. And when looking at these light curves, what I wanted to really be looking at are relative photometric fluxes. So taking the flux of the target and dividing it by a comparison star in order to cancel out systematics in the observations. Now, this proved to be a bit of a challenge because the targets are nearby M dwarfs. They're very bright and very red in comparison to the comparison stars, which were dimmer and bluer. So what that means is that when I took the flux of the target star and divided it by the comparison stars, it wasn't able to cancel out the systematic effects in the observations very well. So what I chose to do was first calculate a light curve where I used one member of the binary as a comparison star for the other. Now they're very good comparison stars for one another because they're super close together on the sky. So systematic effects in the observations are extremely similar between the two of them. And they're also the same brightness and the same color. Now, when I made a periodogram of that light curve, I found that there was a significant periodic signal at around 17 days, which is good to know, but I can't from that alone attribute that periodic signal to either HG 79211 or its binary companion, because the flux from both of those stars has gone into this measurement. So then what I did was calculated two more light curves, one for each of the members of the binary, where I used one of those other comparison stars in the field as the comparison when calculating the relative photometry. And because, as I had mentioned earlier, those comparison stars were not super well suited, there were a lot of systematics left over in the observations. So when I make these periodograms for HG 79210 and HG 79211, a lot of the periodic signals are shared between those two. And those are systematics that were left over in those light curves. But what I found was that there was a periodic signal in the light curve of HG 79211 around 17 days that was not present in the light curve of HG 79210, which indicated to me that this 17-day periodic signal I saw in that first light curve I mentioned, I could attribute it to HG 79211. Also, this rotation period of around 17 days was also consistent with the rotation period suggested by the V sin I measurement, However, because of large uncertainties on the V psi and I measurement and also the radius of the star, that uncertainty is quite large, but it is consistent. Now, the next step in testing if the signal could be caused by stellar activity is to look at different stellar activity indicators. So from the same HARPS North spectra that we use to calculate the radial velocity of the star, we're able to measure a number of other parameters that have been shown to be correlated with the activity on the star, such as H alpha, the full width half max. And here, what I'm doing is showing the periodogram from the radial velocities. So this is kind of a zoomed in version of one of the periodograms that I'd showed earlier, and marking these two significant periodic signals with these green and orange lines, again, as I did earlier. And here I'm also plotting the periodograms of these different activity indicators, stellar activity indicators. So we can go through and scan and see that there isn't a significant periodicity in any of the stellar activity indicators at this 24.4 day period, which is great. If there were, it would be a lot harder to convince ourselves that the periodic signal we see at 24.4 days is being caused by a planet and not being caused by stellar activity. But this here suggests that it is not connected to stellar activity. And the final question is, do we see this 24.4 day planet in all of the available data sets? So to test this, I used a code called PyOrbit to fit a second order polynomial to the three data set baselines, so the high-res, the HARPS North, and the CARMENES data sets, simultaneously with a Keplerian model for the planet and a Gaussian process to model stellar activity to different combinations of the data sets. So here I'm showing the phase folded radial velocity curve of just the HARPS North radial velocities. So it did, I had a pretty open prior on the period, and in this MCMC fitting routine, it did fit a 24.4 day period for the planet with a mass of 12 plus or minus about 2 Earth masses. Next, I did this for the HARPS North radial velocities in combination with the CARMENES radial velocities, again, finding this 24.4 day periodic signal and finding that the mass of the planet is 10.5 plus or minus 1.2 Earth masses, so consistent with the fitting of the HARPS North data set on its own. And finally, one last time, adding the high-res data set, which is plotted here in these black points. Because there weren't so many high-res data points, it didn't make a huge difference in being able to constrain the planet parameters, but it was encouraging to me, at least, that the high-res data sets did not disagree with this planet's presence. So all of this put together equal to me being able to validate this super Earth HG 79211b. So as a follow-up to the González-Álvarez paper, and I published this at the beginning of this year. Now, the last thing that I want to talk about is GJ341, this atmospheric target that I mentioned. This is a planet candidate with a radius of 0.9 Earth radii in a period of 7.6 days that was discovered in test data. It orbits an M0 star about 10 parsecs from Earth, so pretty nearby. And as far as temperate rocky planets, this one has one of the highest transmission spectroscopy SNRs, or predicted SNRs for the transmission spectroscopy, which makes it an ideal atmospheric target. Now I've written here that it has JWST atmospheric observations scheduled. The first observations were taken this past weekend. And although this is just a test candidate, JWST also detected a transit. And so it is, I suppose, now confirmed, or it will be once that gets published. Here on the right, I'm showing the transit fit to the TESS transits for this planet. Now, as I had mentioned early on, we can get really great atmospheric observations from JWST, but it is very important that we also have a mass measurement when trying to interpret those observations for small planets. This particular target has some available public HARPS radial velocity measurements. So 57 HARPS RVs taken over 9 seasons with median uncertainties of just over 1 meter per second. I'm showing those, just the time series of the radial velocities here on the right. Now you can kind of already see by eye that there are other trends in the radial velocities that well dominate over the 7.6-day planet, which is to be expected. We would expect that the radial velocity signal from such a small planet would only be about 1 meter per second or smaller. So I took this whole project as kind of an exercise in testing how small of a planet we're able to detect in a data set like this. So first, to address this dominant RV trend, there were some places in the literature where it was suspected that this target had an unseen companion that was causing this pseudo-Keplerian radial velocity curve. But in looking at the stellar activity indicators, found that this same dominant RV trend was present in a number of the stellar activity indicators. This here is the sodium doublet. Oh yes, so you can see that it's shared there. And I attributed this dominant trend to the magnetic activity cycle of the star. In order to model this activity cycle, I modeled it with a 4th order polynomial following Gomez de Silva et al. 2011, which was long-term RV monitoring of a number of different M dwarfs. So they found that they, in those other M dwarfs, also could see the magnetic activity cycle and modeled it with a 4th order polynomial in combination with the activity indicators. And then it's out of these residuals that we need to model for the stellar activity, as well as adding a Keplerian model for the planet. And I chose to model the stellar activity using a multi-dimensional GP. So that means that I'm fitting the stellar activity model to both the radial velocities and the activity indicators. And that's because even once this polynomial trend was removed, there's still a high correlation between the activity indicators and the radial velocities. Now, as I was sort of mentioning earlier, it's useful to try to determine the stellar rotation period when modeling the stellar activity. And I could not find a conclusive stellar rotation period for this star. Here I'm showing the posteriors of fitting some activity models to the radial velocities, and also breaking up the TESS observations into 2 sets and trying to fit for the rotation period in the out of transit light curves. So this target was observed by TESS in sectors 9 and 10, and also 36 and 37. So when trying to fit for the stellar rotation period in the radial velocities, I ended up with this double peaked posterior with 1 peak around 9 days and 1 peak around 13 days. In sectors 9 and 10 of the TESS out of transit light curve, I fit a rotation period of just over 14 days. And for sectors 36 and 37, again, have this kind of double peaked posterior with a peak around 9 days and a peak around 13.5 days. Now, to place all these data sets in context, I wanted to show kind of a timeline of when they were taken. So these orange points are the HARPS RVs, which were taken between 2004 and 2013. And then we have these 2 pairs of TESS sectors. Sectors 9 and 10 were taken in 2019, and sectors 36 and 37 were taken in 2021. So it's not super surprising that we don't see the exact same stellar rotation period in each of these data sets as spot configurations and things evolve on the surface of the star. It's not surprising that there's some variation there. But something that is encouraging is that this is all consistent with the V sin I, with the rotation period suggested by the V sin I measurement. And the way that I decided to move forward with this in my analysis was that I ran all of my analysis twice, once fitting for a rotation period around this lower end, so between 8 and 10.5 days, and once fitting for the rotation period around this higher end of 10.5 to 15 days. The upshot is that all of the analysis was consistent, no matter which rotation period I adopted, but and in a following plot, you're going to see 2 sets of results for each of the rotation periods. And ultimately, I wasn't able to detect the 7.6-day planet in the radial velocities, which again isn't very surprising. So here on the left, I'm showing the posterior of fitting for the planet parameters in the radial velocity data set. So the period and the transit time of the planet are very well constrained by the TESS light curves and the transit observations. And the semi-amplitude in the radial velocities that I find is consistent with 0, which is a non-detection. And I'm showing the phase folded radial velocities here on the right, but again, semi-amplitude is consistent with 0, and the radial velocities are kind of just a scatter around 0. So the next test to do was to see if I could get an upper limit mass measurement for this planet. The way I did that was by injecting the Keplerian of planets with different masses into the HARPS radial velocities. Also, I may or may not have said HARPS North by accident when talking about this project. They are HARPS radial velocities, so that's my mistake. So I injected a planet mass of half of an Earth mass, and then on the integer value, so 2, 3, 4, up until 10 Earth masses. So in doing this exercise and trying to recover these injected planet signals when varying the radial velocity data within its error bars, was that when I inject a 5 Earth mass planet, I am able to recover that planet 100% of the time. And so here's an example of what that phase folded RV curve looks like. So this is a test that I ran 500 times. Here's just one example where we have an over 3 sigma detection of this 5 Earth mass planet that I had injected. Now, if we compare that to, say, the injection of a 3 Earth mass planet, we're able to recover that about 40% of the time. Here's an example of when I was able to recover this 3 Earth mass planet. And here's an example of when I wasn't able to recover that 3 Earth mass planet, so that other 60% of the time. So again, I'm injecting the same signal, but then varying the data within its error bars when running these recovery tests. So the conclusion here is that I can determine that the mass of this planet is smaller than 5 Earth masses, because if it were 5 Earth masses or larger, I would have found it in this radial velocity data set. And also, if it were 4 Earth masses, what I found is I would have been able to recover that 90% of the time. So in my future work, I'll be wrapping up that previous project that I just finished telling you about. I'm also going to be working on discovering and getting the mass of another rocky planet search target. So this is another HARPS North target that has many years of radial velocity observations in an effort to detect smaller planets that haven't been found to transit yet. And I'm also working on a HARPS North data set, which is an RV follow-up for a single TESS transit. So in that case, we're using the radial velocities to help constrain the planet's period, as well as its mass, and searching for additional planets in that system. And all of this is ultimately trying to push toward finding the masses of cooler, smaller planets using both high precision radial velocities and increasingly sophisticated stellar activity models. Thank you very much for listening, and I'm happy to take questions.
Thank you very much, Victoria, for such a nice talk. Please, if you have questions, you can raise your hands or you can write them down in the chat and I'll read them, or Victoria will read them herself. So I wanted to ask you about the first planet you talked about. This was in a binary system. I'm assuming it's a white binary, right? So yes. Do you have the data to measure the inclination, and is that aligned to the binary system, or?
Oh, that is a good question. Yeah, so we were not able to measure the inclination of the planet.
Okay.
Yeah, but I know that there's been interesting work recently about how like the orbital alignment or misalignment between stellar binaries and their planets.
Which is the separation between the two components?
130 AU.
Okay. Okay, thank you. I'm seeing a hand raised now, so Esther, please go ahead.
Hi, Victoria. I am Esther González, and I am the first author of the discovery paper of GJ338b. And I want to ask you some question. For example, when you use the HARPS data, you also analyze this data separately from CARMENES. And I want to wonder, because when you show the GLS periodogram, I think that the range covered is not cover the 16 range days. That is the rotational period of the star published in the article. So I wonder if you see the rotational period, or maybe the first harmonic of this signal in your only HARPS data.
Yeah, so I did not actually. So it is true, I didn't show that in my periodogram. I did not see any significant periodic signals at shorter periods than what I had shown, which I found curious. I kind of explained this to myself as perhaps there was some kind of, what do I want to say? Like that in the course of the longer baseline observations, if it's possible that based on changing spot configurations, if that periodic signal could have been squashed. I'd be curious if you have any thoughts on this, because that was something I found curious as well.
Yeah, because in the rest of the activity indicators that you analyze derived from the DRS of HARPS, you didn't see any signs of activity at 16 days, right?
That is
neither
a good question.
In radial velocities and neither in the activity indicators, nothing at 16 days.
So I definitely didn't see it in the radial velocities. Let me double check what I had in the activity indicators.
Because the possibility or the explanation that you expose now, I think that is not really true, because you can see that the time coverage of the CARMENES data and HARPS overlap in time. So the stage of the stellar activity in this moment should be the same in both cases. So I wonder if you also see the stellar activity effects in your data.
Yeah, so well, I can also, let me share this. So this was from the paper itself, and the only activity indicator that had a significant peak in the neighborhood of 16-17 days was the bisector inverse span. And I had also tried to analyze just the HARPS North the HARPS North data that overlapped with the CARMENES data. And unfortunately, there just weren't enough HARPS North data points to get a converged result using just those seasons, because there were so many fewer points per season.
Okay.
Yeah, so I couldn't make the direct comparison.
And I don't know if you also take some additional photometric observation in order to corroborate the stellar rotational period or something like that, on how you fit your GP model to the radial velocity. Only fix the rotational period at the value published in the paper, or you let free the stellar activity model, or?
Yeah, so I used a quasi-periodic Gaussian process kernel. I constrained the rotation period to, let me pull this back up. So when I discussed the, here it is. The photometry that I was able to get, I set a Gaussian prior on the stellar rotation period using the median of these ranges. So both the peak in the light curve I found by using each of the members of the binary as a comparison for the other, and for HG 79-211 separately. So basically, my prior for stellar rotation was in these regions around 17 days. But it was approximately 16 to 18.
And the final value that you obtain from your GP model is consistent with that published at 16.6 days, right?
Yeah. So I think I got, like, what I found was slightly higher, closer to 17 days, but quite close.
And just the last question, do you consider that using only the HARPS data, do you have a robust confirmation of this planet?
Yes. So, I mean, the detection is, I should probably know the sigma value off the top of my head, but I do not. Yeah, so it's like, what is that like?
Yeah, the data fits very well with the Keplerian orbit, but in this plot, you subtract previously the activity of the star, right?
Yes, I fit it all. So I fit it all simultaneously, but it is subtracted in this plot.
Okay. Okay, thank you.
Okay. Also, I'm excited to see you. I have read your paper many, many, many times.
I suppose. Thanks.
Okay, I don't see any more questions. So yes, so I have to thank you again. Thank you very much for being here. I hope next time you can make it in person. And thank you, everybody. See you all next week.
Thank you, everyone, for listening to me.
Thank you, Victoria. Bye.